Hello. So we're doing lab again. So let me, before we launch into today's lab, let me ask a couple of things. Are there any questions? Do you guys have any questions about anything? I have a couple things for you. I did post this, I think, in the announcement. Let's see, I posted the video from Tuesday's lab, and I did post, there's a correction for the analysis. All right, so the torque calculation assumed the frictional force was equal to the component of weight that points down the incline, but that can't be true because it's the center of mass is accelerating down the ramp as the, remember you had this guy rolling in a tape roll. The frictional force is actually smaller than that component of weight, and you can correct for that by solving Newton's second law in that direction and relating it to the acceleration, angular acceleration to the center of mass acceleration. I did that. At the end of that video, I put that analysis in there, and so that equation is in that handout, or sorry, in that video. So use that to analyze your data. What it should do is reduce your experimental moment of inertia. It should make it closer to your theoretical. Does that make sense? Cool. Let's see, what else?
I had a quick question.
Yeah, Sarah.
For today's lab, there was like the second handout that's got like, you know, the part 1, part 2, and like the fill in the blanks. Is that what we're turning in for this lab's
yes,
report instead of the actual written out one?
That is correct. Yeah, today's lab has a worksheet that goes with it, and the intention is for you just to fill out the worksheet and turn that in instead of writing a full write-up. So if you really want to do a write-up, you can do that. But yeah, if you just fill out the worksheet, and if you don't have the ability to print the worksheet, or if you simply do not want to, you could just answer those questions separately. I did put a file upload spot for this lab for you to turn that lab in. So again, it can be this filled out. I mean, frankly, you could fill it out in the Word document and save it and upload that. That would be totally fine. Other questions? Cool.
If we
did
a write-up, would you give us extra credit?
Oh, sure. And now the students who are intending to take the MCAT now think they've got to do the extra credit. You'll be fine. Everything's fine. There's no A++ in this course, so it's just okay. Yes, so that is the official answer is yes. If you upload a full write-up for this, I will give you extra credit. I have not determined how much extra credit it'll be, but I'll give you some. Why not? Other questions? Okay. So what are we doing? We are playing with springs. So there should be a spring that came with your IO lab, right? Let me caution you against stretching this too far, right? Because this is metal and it does have an elastic limit. And if you go further than that, it won't spring back, right? Also, yeah, if you've ever given a slinky to a child, you're aware of like, oh, slinkies are great, but they don't always go back to their original spot. Let's see, two years ago when I taught this, was that 2 years ago? It may have been last year. When I taught this course, there was a student in the class who did not know what a slinky was, had never seen a slinky. So I got the privilege of introducing him to the slinky. It was, was no small thing for me. It's pretty awesome. Okay, so you're going to do two things for this lab, really. It says part 1, part 2, part 3, but really part 1 is one thing, and parts 2 and 3, part 2 is data gathering, part 3 is the analysis of part 2, but it's more complicated than the analysis for part 1. So you're going to attach this to your IO lab. You're going to need the force sensor, all right, because part 1, you're verifying Hooke's law, right? So remember, Hooke's law for a spring is F equals minus K delta X. So you're going to attach this to your force probe, set it on the wheels, right, and then pull it back and forth, and you're measuring displacement here and force here. So you can plot force versus displacement, and the slope of that should be your spring constant, right? Again, when you say plot this versus that, you're generally saying Y versus X. So if you plot force versus displacement, you should get plot force versus displacement. Force is on your Y-axis, displacement is on your X-axis. So for those of you keeping track, you can do, I think you want to do a parametric plot for that and put your force on the Y-axis. That's great. The app I use to transfer files from the iPad to my computer is free with ads, and that's what you just heard was one of the ads. So let me do something else. So the second part of this lab is you're going to measure period for a mass on a spring, right? So let's do that quickly. And frankly, I'm not sure. I'm not sure how the write-up suggests that you get this, but there are a couple of different ways. So you're going to do this. You're going to hang your spring, right, by something. A binder clip would be excellent. Let me grab one. Here. So I have a binder clip. You could clip this to like the edge of a table or something. So you can clip this to the table, and then you can let this oscillate, right? And you can get a period out of this by looking at, you could look at the force versus time data, you could look at the acceleration versus time data. Either one of those should get you an oscillating thing. Simple harmonic motion is chapter 13. It'll be in chapter 13. So we're not quite there, but you can do this analysis easily enough. So grab that period. So that's going to be, let me share my screen with you. And I just need Scratch, not that Scratch though. Okay. There we go. Okay, so you're gonna see a plot that looks kind of like this, right? For, let's say, acceleration versus time. It would also be the same thing for force versus time. It would be, I think it'll be inverted, but it doesn't matter. What you want is the period for this motion. So remember, period is the time it takes something that is cyclic to repeat. All right, let me say that again. Period is the time that it takes a cyclic process to get back to where it started. So for this, you've got this guy oscillating from, right, from its peak position to a low position and then back to the peak position. So top back to top is one cycle, right? You could also say middle back to middle or bottom back to bottom. Top to top is a nice way to visualize it though. So then the period on this plot is like peak to peak. So the distance from here to here, that is period. We use a capital T for that. All right, and it turns out for a mass on a spring, the period of that motion is related to the mass of the oscillating thing and the spring constant. It's 2 pi times m over the spring constant. The write-up says k sub s. That is because when we talk about waves, there's another k that is wave number. So k sub s is just spring constant. Okay, so we do this here. Oscillating mass and spring constant. And again, this guy is just period. If you put everybody in SI units, the period comes out in seconds, right? That's the SI unit. Okay, so far so good. Questions? Again, I'm just giving you this equation for now. I'll probably derive it when we get to chapter 13. It'll probably be in a pre-lecture video. So you got that to look forward to. I know, hate to keep you in suspenders, but okay, so you could measure the period. You could measure period, right? Because you can get that from this graph, right? For several different masses, right? And again, your IO lab should be roughly 200 grams. So that's 0.2 kilograms. And as I said last time, mine actually is. I thought it wasn't, but I was wrong. So that's one data point. I'd like you to get several though. So you could add stuff to this plus more mass. And I think the write-up has like AA batteries taped to the thing. Yeah, I think that's a great idea. So you're going to need something you can use as a mass. And again, you can use, now that we know the force sensor won't measure the mass of the force sensor itself, right? And that kind of makes sense. You're asking it to measure itself. But if you put the, you could even hang it, right? You could tape the extra mass you're going to use. If you had, let's say, a pack of several batteries, I happen to have some right here. You could measure the mass of one of them by like taping it to the force probe. And then you could say, okay, I could add 1 to this, I could add 2 to this. AAAs aren't great because AAAs don't weigh very much. But I think I've got it. Here's a dollar store 9-volt battery. You could use that. Or anything, right? I've got a flashlight here, another flashlight here, another flashlight here. Another flash. I have all the flashlights. I have Pez. Oh my, I have Pez. Anyway, you're going to add mass. So you can add several different amounts of mass, and then you'll end up with a set of periods versus mass. And those should allow you to get the spring constant. But you know, so you could calculate the spring constant for every one of those, right? That's one way you could do this analysis. But what I would prefer that you do is plot it. Man, I made a hot mess of this up here. There, that's better. I would prefer that you plot it and then fit it. So this I would do like in Excel or Google Sheets. So how do you plot? How do you plot this and fit it? Well, if you just plot period versus mass, it should be, it's a square root relationship, right? That's kind of terrible. But if you plot period squared, that would be related directly to mass. And that's where this expression comes from. Again, if you look in the, yeah, basically, if you take that relationship, period equals 2 pi root m over k, and you square both sides, you get t squared equals 2 pi squared times m over k. And if you move that over the over k, you move it over here, then you could say, well, look, if I do this, let's see what color, y equals slope times x. If you plot t squared as y and mass as x, then your slope equals 2 pi quantity squared divided by the spring constant, right? So that lets you plot a straight line and get something that's proportional to the spring constant. So then you will have measured the spring constant in 2 different ways, using Hooke's law and using oscillations. And then I think the write-up says to look for your percent difference. I'm not a huge fan of that, but that's fine. That's what's in the write-up. You can just do that. The bottom line question is, are they equal, right? And you need uncertainty to figure that out. But you don't even have to do a write-up here. So you can just do a percent difference, and we'll call that good for a summer course. So let me pause and ask, does this make sense? Do you have a sense of what you're doing? I think this is kind of a cool lab. Maybe the most challenging part is finding mass to tape to your IO lab. I don't care what it is. Really, you're just looking for, if this is 200 grams, it'd be nice to up that by, I don't know. I don't know that you can go up past like a factor of 2 because you don't want to stretch the spring past its elastic limit. Yeah. So I think I would just say be reasonable with it. All right. Okay. So unless there are any other questions, I'll just get you guys started. How many groups should I do today, you guys? That looks great. Okay. So let me know if you have questions.